Hi everyone. This video is to go over the steps on how to change something that is an entire radical into mixed radical. So first of all, what does entire radical and mixed radicals mean? Entire radical means when your radicand is underneath the square root or cube root and there is no number in front of it. So this is complete entire radical. And when we simplify it, it will actually be able to take out numbers outside, and now you can see there's a coefficient in front of it as well as there's a radicand. So this form itself is called a mixed radical. So our first job is to see how do we take these big numbers and we simplify them. So these are simplified versions, and make them into simpler ones. Sometimes some of these numbers will just become a whole number altogether, and there won't be any radical left. And in other times, you will see that it will simplify to something like a mixed radical. So it's very similar to like what we do with fractions. So sometimes when we have a number in fractions, we try to simplify it, like 10 divided by 2, and it ends up being just a whole number, 5. There is no denominator left there. But in other times when you are trying to do that, let's say if you're trying to simplify 30 over 45, when you simplify and reduce it, it will become 2 over 3. So we were able to reduce it, we were able to keep dividing it out, simplifying it out, and we did end up with a simpler fraction, but we did still have a numerator and denominator. So that complicated form is the entire radical form, and when you simplify and you're able to take some whole numbers out, is called a mixed radical form. So we need to be able to get to the most simplified mixed radical form there is, just like we always like to always bring our answers down to the simplest fraction, the lowest terms. We also want to do the same thing with radicals. We want to simplify it to the lowest form. Okay, so how do we do this? In Math 10C, you have done this, and you have used prime factorization method where you break down a number and until into its prime factors. You can continue to use that method. So for example, if you were trying to find 20, you would break 20 down to its prime factors using a factor tree or any of the other methods you have used, like this one, where you keep dividing by prime numbers until you get all the way down to 1. So this was a method that you used in Math 10C, and because this is a square root, you try to make it into groups of 2's, and then you leave that one that doesn't have a group inside. So when you make a group of 2, and the reason you made 2 is because it has an index of 2, only 1 comes out, and this 5, because it couldn't have a buddy, it stayed inside the radical sign. So that would be the simplified version of root 20. It would be 2 root 5. Okay, so this is the prime factorization method, where you find all the prime factors, and you probably did this in Math 10C. The method that we're going to learn in this class is using your perfect square table. And the reason we do that is because it's faster, a little bit harder sometimes to learn, but definitely faster. Okay, so it will take a time, but I can give you some tips on how to do that. There's nothing wrong to keep using prime factorization, but like I said, it will just take you longer to do those questions. Okay, so this is the first example here. So I'm going to do the same thing, which is the square root of 20, but I'm going to be using a perfect square root table that is right here. So this table, you can very quickly make on your own. It's simply just taking your numbers and squaring them. So 1 squared, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. So this gives you the perfect square root table right here. Okay, and what we do is we focus on these numbers right here. These are the numbers that we're actively looking at. okay? Because if I were to take a square root of any of these numbers, they would just give me that number that I multiplied. So the square root of 4 is 2, and the square root of 9 is 3. The square root of 16 is 4. These are the numbers that we want. We want to see them, and so on, okay? Now, the number that we have here is square root of 20. And what I want to do is I want to split that 20 so that one of the numbers is a perfect square root, one of these ones that I can see from the table. So looking at it, the way to split 20 would be by 4, because 4 times 5 is 20. And I want to pick that first number to be a perfect square root. And the reason is I can take this and rewrite that as square root of 4 and square root of 5. Now square root of 4 is important because this is a perfect square root. That means if I take a square root of it, it does give me the answer 2. So I was able to take that 2 out. So it became 2 root 5. Because root 5 I cannot split any further. There's no perfect square root that will multiply to give me 5. So 1 times 5 is kind of useless because 1 doesn't really change the 5 then. So the answer to this becomes square root 5. Okay. Let's see if I can do another example here. I am going to do another one. So this is not in the book. So what if I have square root of 75? So the idea here is to split the 75, and I want that first number to be a perfect square root. Now, I could check with my calculator if there's any number here that 75 can divide nicely with. So if I try going and I say, okay, I'm going to try 75 divided by 9, well, that gives me a decimal. That doesn't work. How about by 16? So again, decimal. How about a 25? So eventually you'll start to get better because 75 and 25, if you think about it, they both should be at the end with a 5. So they're divisible by 5. That works. So 25 is the number that I'm looking for. So I'm going to rewrite this as 25 times 3 because that's what 75 is. And I on purpose picked 25 because it is a perfect square root. So this, if I take a square root of 25, it will give me a 5. Root 3, I can't do anything, so I'm just going to leave it as it is. So this method is using the perfect square root table. Again, you can use prime factorization, but with practice, this becomes a much faster way to do your roots than to use prime factorization, which ends up having a higher error rate because you see so many of the same numbers. So very easily you can miss one and make a mistake, whereas this one, it's usually just 2 numbers. Now, you can do examples in the book to see if you are comfortable with this. The next thing I want to talk about is what if the number is bigger? So like 20, 75, they're numbers which can have different options. So before I do that, I want to talk about an option where we talk about same thing in fractions one was talking about. Remember we talked about that in fractions you can have 30 over 45, you can reduce it. So one way you can reduce it is by step. Say you can say I'm going to divide this by 5, which gives you 6 over 9. And then you notice, oh, well, I did reduce it, but it's not in the lowest term. So you go ahead and divide it one more time, actually by 3. And that gives you 2 over 3. And you're done. So you had to do this twice, but you did get this lowest form. So it's important to keep going until you get the lowest form. And sometimes if you're lucky and your brain is just in the right spot, I can say, hey, why don't I just divide this by 15? You were able to get the greatest common factor and it gave you the right answer, boom, in one step. So sometimes we have to do two steps, and sometimes we get lucky and we can do it in one step. But the correct answer is still there, so it doesn't really matter. And that's the same thinking that we have to keep in mind when we have some numbers like they're trying to show us here, which is square root of 72. So when there's 72, sometimes you're lucky and your brain will zoom right to the biggest number that you can divide it by, which is a perfect square root. And lucky you, 36 times 2, and root of 36 is 6 root 2, and you were done in one step. You're like, ooh, easy question. But other times your brain's like, well, it's not really seeing 36 right away. It will see 4. And that's perfectly okay because 72 divided by 4 works. It does become 4 and 18, and 4 was a perfect square root. So you're like, this is good. This is legit. This gives me 2, and that's root 18. So your final answer here came out to be 2 root 18. But that's just like reducing fractions, just like that 6 over 9. We're not done yet. So if this number is still big enough, go back and see if you can break this one again. Leave that 2 where it is. You were already brought it out, but now you're going to split that 18 even further if you can. And in this case, 18 can be now divided by a 9, which is another perfect square root, and that will give you the 3. So the 2 just comes down as it is. We're able to get the square root of 3, which is 9. And now finally, this 2 is the smallest one that we cannot break down. So any numbers that you have outside, they multiply. And this becomes 6 root 2. The same answer, but we did it in a few more steps. Okay, so it's perfectly okay, just like here. It's perfectly okay to do it in multiple steps or in one step, as long as we make sure that we get it to the simplest form. If there's a number outside already, don't worry about it, leave it there. You just continue with trying to split this number. So again, you're going to try dividing this by these perfect square roots. You could start with a 9. It may not work, or 16, or so on. And it does take a few tries, but eventually you're going to find out that it is actually going to get split as 49 times 2. So the 3 that was outside stays here. 49 gives me a 7 times root 2. So this answer becomes 21 root 2. Okay. There is an extension bit as how to do the same thing using a cube root. Well, you make a new table using your cubes. So this time you just go 1 times 1 times 1 is 1, 2 times 2 times 2 is 3, and so on. And we use the exact same thing here. What number can we divide this 40 by? That's in this table, because this is a cube root table now. And this number is in 8. So the cube root of 8 is 2. The 5 we cannot do anything. So the final answer is cube root of 2 cube root of 5. So the only thing that changed here is that we had to make a table of perfect cubes because this was dealing with the index of 3. Okay. I will talk about what to do with if you ever see anything with a higher index like a 4 or 5. Then we try to do it a slightly different way. We don't really see a lot of those in math. It's mostly square roots and then a little bit of cube roots here and there. So it's good to practice both of them. Again, please go through your Moodle workshop books to do the rest of the examples.